Units and conversions. Let us study that. So in the subject of physics, we have to define a number of physical quantities. The laws and principles and concepts of physics are expressed using these physical quantities, right? So let us study the properties of these physical quantities. Now let us see what is measurement first. What is measurement? So measurement is the comparison of an unknown quantity, as you can see this is unknown quantity, with a known standard quantity. So for example, this is a known standard quantity, that is a meter scale. We know how much is the length of a meter scale. Let's say suppose this is of, let's say, 5 meter. Now you can easily measure the length and the width of the vehicle or a bicycle here, which is an unknown quantity. So that term is called as measurement. So measurement is the comparison of an unknown quantity with a known standard quantity or unit. Next, what is magnitude of physical quantity? So magnitude of physical quantity is nothing but, there is a physical quantity, let us assume it as your length. Yes, so length is, suppose how we can express length? We can express length in terms of magnitude and its unit. What is the magnitude? It's just a number and the unit is meter. So the length comes out to be physical quantity, 5 is the magnitude and meter is the unit. So this is the magnitude of a physical quantity, right? Fundamental quantities. Fundamental quantities. So fundamental quantities are those which are independent of other quantities. The basic and foremost property is they are independent of the other quantities, right? So there are 7 fundamental quantities here, that is mass, length, time, temperature, electric current, luminous intensity, quantity of a matter. So the unit of mass is the unit of mass is kg, length is meter, time is second, temperature is Kelvin, electric current is ampere, luminous intensity is candela, and quantity of matter is mole, right? So these are the fundamental quantities. So the physical quantity which is independent of any other quantity is called as fundamental quantity. That is mass, length, time, temperature, electric current, luminous intensity and quantity of matter. These are the 7 fundamental quantities identified by physicists. The 7 fundamental quantities as mentioned over there, that is mass to quantity of matter, they are termed as 7 dimensions of physical world. And any other quantity can be expressed in terms of these 7 fundamental quantities, right? Good. Now let us study fundamental unit.
Any physical quantity, such as length, mass, or time, is measured and denoted in terms of their standards, called a unit of measurement. A unit is an internationally accepted basic reference standard against which the measurements of any physical quantity are compared. In physics, we deal with many physical quantities and their units. However, very few basic units are required to express these physical quantities. Most physical quantities are expressed in terms of some base quantities. These base quantities are referred to as fundamental quantities. For example, distance, which is a measure of length, is a fundamental quantity. It's the same with time. The other quantities which are expressed in terms of their fundamental quantities are called derived quantities. For example, area or volume, which is expressed in terms of multiples of length, is a derived quantity. Similarly, speed is a derived quantity as its measurement depends on distance and time. The units of fundamental or base quantities are called base units or fundamental units. The units of derived quantities are expressed as a combination of base units. Such units are called derived units. Base units and derived units together make up a system of units. A system of units is a generally accepted set of units of measurement. Until recently, 3 major systems of units were in use in different countries based on the units of 3 fundamental quantities, namely length, mass, and time. Among these were the CGS system, which stands for centimeter, gram, second, and FPS, which stands for foot, pound, second, respectively. These units are adopted by Britain, and hence the system is referred to as a British system. The third system of units is the MKS system, which stands for meter, kilogram, and second. However, in 1971, the General Conference on Weights and Measures recommended a standard set of units of measurement with their symbols and abbreviations. This system is known as Système International des Units, French for International System of Units, abbreviated as SI. Currently, SI units are followed globally for all scientific, academic, commercial, technical and industrial purposes. In SI, there are 7 base units for the 7 physical quantities taken as fundamental quantities. Following are the quantities and their corresponding units. Length is measured in meters, denoted by the small letter m. Meter is the length of the path travelled by light in a vacuum during a time interval of approximately 300 millionth of a second. Mass is measured in kilograms, denoted by the small letters kg. Kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures at Sèvres, near Paris in France. Time is measured in seconds, denoted by the small letter s. A second is the duration of approximately 9 billion periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of the cesium-133 atom. Electric current is measured in ampere, denoted by the capital letter A. An ampere is that constant current which, if maintained in 2 straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 multiplied by 10 raised to the power -7 Newton per meter length of the conductor. Thermodynamic temperature is measured in Kelvin, denoted by the capital letter K. A Kelvin is a fraction 1/273.16 of the thermodynamic temperature of the triple point of water. luminous intensity is measured in candela, denoted by the small letters CD. A candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 power 12 Hz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian. An amount of substance which contains as many basic entities, such as atoms or molecules, in a system as equivalent to the number of atoms in a carbon-12 isotope is measured in mole, denoted by the small letters.
Fundamental unit. The unit which is independent of any other unit is called as fundamental unit, right? So which unit is independent of any other unit? Now as we can say what is mass. Suppose mass of a person is, let's say, 50 kilograms. Now this kilogram is nothing but called as fundamental unit, right? So this fundamental unit is called as fundamental because it is independent on any other unit. So kilogram is not dependent on any other unit for its definition, right? That is why it is called as fundamental. Similarly, there is meter, there is second, that is time, there is Kelvin for temperature, ampere for electric current, candela for luminous intensity, mole for quantity of matter. So these are the fundamental units. Now there is another term, that is, we call it as derived quantities. What are derived quantities? Now if you pay attention on the word, there are some quantities which are derived. So what do you mean by derived? Derived is nothing but using some other thing we have obtained the particular derivation here, right? So that's why the physical quantity which is derived from fundamental quantities, let's say we have some fundamental quantities, and from those fundamental quantities, we have derived some physical quantity. So such kind of quantities are known as derived quantities because they are derived from fundamental quantities. They are coming from fundamental quantities. That's why they are known as physical quantities which are derived, hence known as derived quantities, right? Now there are quantities, so obviously for any quantity there will be an unit. So similarly for the derived quantities there are derived units. Right? So the unit which depends on fundamental unit is called as derived unit. So let us take some examples. So speed, for example, speed, velocity, acceleration, right? So these are nothing but derived quantities, right? They have a specific derived units. So they are force, etc. So these are what? Derived quantities. So for this derived quantities we will be having some units. So what are the units of velocity? Or you can say speed. There will be unit of meters per second or kilometer per hour. So these meter per second and kilometer per hour is nothing but derived unit because we have derived it from fundamental meter and fundamental second, right? Similarly like kilograms and all, right? So here you can say meter, here you can see second. So meter and second से हमारा बना है meter per second. That is why it is called as derived units. right? Yeah. Now the definitions of 7 basic SI units. Let us study the definitions of 7 basic SI units. Definitions of 7 basic SI units. Right? So what are the 7 basic SI units? First is meter. What is meter? The meter is a basic unit of length. Meter is basic unit of length. Second, what is the second basic? Kilogram. What is kilogram? All of you know kilogram is kg, which is the basic unit of mass. It is a basic unit of mass. Third is second. What is second? Second is nothing but basic unit of time. Basic unit of time. Yes. Fourth, ampere. Ampere. That is basic unit of electric current. Electric current. Fifth, Kelvin. Kelvin K. What is that? Basic unit of temperature. Mole. The basic unit of substance. Basic unit of amount of a substance. Last but not the least, seventh, candela. Candela is nothing but CD, which is the basic unit of luminous intensity. Luminous intensity. So these are the definitions of 7 basic SI units. Right? Now, what is SI? Let us turn. What is SI? SI का मतलब क्या है? Let us try to understand this using the system of units in the next concept. System of units. So first system is CGS. CGS, let me explain. CGS system. So here in this system, C stands for centimeter. Centimeter, that is of length. Then G stands for gram. G stands for gram. And S stands for second. S stands for second. That is time. This is mass. Right? So this system is generally adopted for smaller measurements of. This system is generally adopted for smaller measurements. So whenever we have to do smaller measurements, like in very small magnitude, we use this system for mass, length and time. Right? This is a CGS system. Next is MKS system. What is MKS? MKS is, M stands for meter, right? K stands for kilogram, and S stands for second, that is for time. This is for mass, and this is for length, right? So this system is generally used. This system is generally adopted for larger measurements. Yes, and last is your SI, जो हमने अभी बात किया था, SI system, that is Standard International Systems. Standard, S for standard, I for international system. Standard International System. So this system is widely used in all the books, and it is practiced by all the physicists, scientists and engineers in different companies. In this system, the units of mass, length and time are same that was MKS system. So it is same, right? All the SI units have been provided. Yes. So for example, for the ampere, it is A. That is, ampere is for electric current, right? Kelvin is for like temperature, meter is for length, mole is for amount of a substance. Such kind of, you can find it as the Standard International System is nothing but a replica of MKS system, that is meter, kilogram, second, and they are also used for larger measurements, and this is widely used in all the engineering work. Yes, good. Let us solve some problems.
The hour, minute, hour, day, year, degree, liter, ton, carat, bar, curie, roentgen, quintil, barn, hour, hectare, and standard atmospheric pressure. For all derived quantities, their units are derived from these base SI units. As SI units use the decimal system, it is easy to convert or derive units from base units in this system. You can easily
solve examples. Example number 1. Calculate the volume of a cube. Calculate the volume of a cube of side 2 centimeter in cubic centimeter. So this has been asked. Express the answer in cubic meter. Express the answer in cubic meter. Yes, so how to do this solution? Let us solve it together. Now, what is the volume of a cube? Everybody knows that. If suppose this is a cube, let's say of side. Suppose this is a cube, right? The side of the cube is given to be 2 centimeter. Correct? Now what is the volume of a cube? The volume of a cube is given by side into side into side. That is the entire volume. Now what is this? 2 centimeter of one side, 2 centimeter of another side, 2 centimeter of third side. This will be 2 cube into centimeter cube. This will be 8 centimeter cube. Right? Now what is centimeter? 1 centimeter means what? Centimeter, 1 centimeter means 10 raised to minus 2 meter. So therefore this will be equal to 8 centimeter cube is nothing but 8 into centimeter is what? 1 into 10 raised to minus 2 meter whole bracket cube. This is equal to 8 into 10 raised to minus 6 meter cube. So the final answer is 8 into 10 raised to minus 6 meter cube. Because we have to express the answer in cubic meter. The radius of the earth, next question. The radius of earth is approximately 6.37 into 10 raised to minus 6, 10 raised to 6, sorry, not minus, meters. Find first question, circumference in kilometer, circumference in kilometers. Second, the surface area in square kilometers, surface area in square kilometers. First, yes, what is the circumference of the earth? Circumference is given by 2 pi r, right? So substitute the value 2 pi into radius is 6.37. It is given 10 raised to 6 meter. What will be the answer? It will be 4 into 10 raised to 7, right? So we have to find the answer in kilometer, right? So let us do it in this way. Now this is 2 pi into 6.37 into 10 raised to 6 meter. So what is this? 2 into 3.14 into 6.37 into 10 raised to 6 meter. So this will be approximately equal to 3 2 is 6, 6 6 is 36. This will be approximately equal to 40 into 10 raised to 6 meter, approximately, right? So this will be equal to, you can write 4 into 10 raised to 7 meters. This meter can be written as 4 into 10 raised to 7, 1 kilometer upon 1 kilometer. It doesn't matter because 1 kilometer cancels out, right? So now this equals to 4 into 10 raised to 7 kilometer upon 1 kilometer is 10 raised to 3 meter. 3 को ऊपर लेके जाओ, 4 into 10 raised to 7 minus 3 kilometers. So this comes out to be 4 into 10 raised to 4 kilometers. Simple answer. Yes, this is the answer of first. Second, surface area. How to find the surface area? Surface area in square kilometer. What is the surface area of sphere? It is 4 pi r square. It will be 4 pi into r, 6.37 into 10 raised to 6 meter whole bracket square. Solve this. Solve this. You will get 4 pi into 6.37 whole bracket square into 10 raised to 12 meters. Right? So this will give you this is 4 into 3.14 into this is 6.37 into 10 raised to 12, this is square. So if you calculate this, you will get 0.9 into 10 raised to 12. This is 5.099 into 10 raised to 14 meters square. Please see. Right? So 1 meter square can be written as, again, this is 5.099 into 10 raised to 14. It can be written as 1 kilometer square upon 1 kilometer whole bracket square. So this can be written as 1 kilometer. So 1 kilometer is 1000 meters. So this is 5.099 into 10 raised to 4. 1 kilometer whole bracket square upon 10 raised to 3 meter whole bracket square. So this is 14, sorry, 10 raised to 14. So 5.099 into 10 raised to 14 upon 10 raised to 6 kilometer square. So answer will be 5.099 into 10 raised to 8 square kilometer. This is the final answer. 5.099 into 10 raised to 8 square kilometer. Because when the downward is 10 raised to 14 upon 10 raised to 6. This 10 raised to 6 will go up and 14 minus 6 will become 8. Therefore 5.099 into 10 raised to 8 square kilometer. Yes, please check. Here I will again repeat, surface area is 4 pi r square. 4 pi into r, this is the radius of the earth. Right, 6.37 into 10 raised to 6, it is given in the problem. So 4 pi into 6.37 square into 10 raised to 6 square is 10 raised to 12 meters. This will be 4 pi, pi is 3.14 into 6.37 square. Calculate this entire value, you will get 509.9 into 10 raised to 12. 10 raised to 12 is this one. So 5.099 into, shift the decimal, get 10 raised to 14 meter square. So 1 meter square can be written as, you can multiply it by 1 kilometer square, divide by 1 kilometer square, this is one and the same, right? So 1 kilometer square, we have to find the answer in square kilometer. So let us convert the downward 1 kilometer in 10 raised to 3, that is 1000 meter. So 1000 meter square. This is as it is. As it is, downward will be 10 raised to 3 square is 10 raised to 6. This 6 will go up, 10 raised to 14 minus 10 raised to 6, that is 10 raised to 8. Final answer is 5.099 into 10 raised to 8 square kilometer.
About different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity, and acceleration is the derived quantity, which is the ratio of change in velocity to time. Velocity, which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression for force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L and time by T. The other four base quantities are represented by symbols of their SI units, namely electric current by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus we can write the expression for force as force is equal to mLT power -2 as shown. Such an expression for a physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula is called a dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length, and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0. In mechanics, Most derived quantities are related to only the three base quantities of the seven, namely mass, length, and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square, and hence its dimensional formula is L power 2. We know that the dimensional formula of force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is the product of length, breadth, and height. Height also represents the base quantity, length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is mL power minus 3. So far, we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube, respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of two identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is the ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and is significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering the medium at a given angle of incidence. Refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constants, each of which has a unit as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtain the dimensional formula of G as m power minus 1 L power 3 T power minus 2. You will learn about G in detail later in the course. So far, we have discussed physical quantities which are expressed as the product of base or other derived quantities. We also learnt that a dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So, we get length. Again, it is not 2 times L as we are not adding the magnitudes of the length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course. We learnt earlier about the dimensions of some physical quantities. The dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. An expression for a physical quantity in terms of its base quantities is called the dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. We will now learn about the uses of these dimensional formulae and dimensional equations. We know that a dimensional equation is the equation among the dimensions of a quantity and not among the magnitudes. Thus, when we write L plus L, as shown, we mean length added to length. So we get length again. It is not 2 times L as we are not adding the magnitudes of the length. This property of a dimensional equation can be used to check the dimensional consistency of equations by analyzing the dimensional formula of quantities on both sides of the equation. For example, consider the motion of a body moving with an initial velocity u and uniform acceleration a, having made a displacement s in a time interval t. The motion of the body can be represented by the equation s is equal to ut plus half at square. Let us now verify the consistency of this equation using dimensional analysis. On the left-hand side of the equation, we have displacement s. This is basically length and its dimensional formula is L. On the right-hand side of the equation, we have 2 terms, each involving the product of 2 different quantities. The first is ut and the second is half at square. When the magnitudes of two or more physical quantities are multiplied, their dimensions are also treated in the same manner as done with ordinary algebraic symbols. In this case, in the first term, it is the product of velocity and time. The product of the dimensions of these quantities is Lt power minus 1 into t, as shown. On simplification, we get L. The second term on the right-hand side of the equation is half at square. Half is a constant and thus does not have any dimensions. In the first term, it is the product of acceleration and time square. The dimensions of A are Lt power minus 2 and that of t are t. Thus, the dimensions of at square are as shown. Taking the dimensional formula of the physical quantities in both the terms on the right-hand side of the equation, substituting their corresponding dimensions and simplifying, we find it is equal to L, which is the dimension of length as obtained on the left-hand side of the equation. Thus, the dimensions of the quantities on both sides of a given equation are the same. This proves that the equation is correct. It is very important to note that physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. This principle is called the principle of homogeneity of dimensions and is useful in checking the accuracy of an equation. This principle can also be used to derive expressions for physical quantities if the other quantities on which it depends are mentioned. For example, we can derive an expression for the time period of a simple pendulum, assuming that its time period t depends on the length, mass of the pendulum, and the acceleration due to gravity at a given place. Let us take the constant of proportionality k as 2 pi. We assume that the time period is proportional to L power A, M power B and G power C, where A, B and C are constants. Replacing the proportionality symbol, we get a constant k. Hence, the time period is equal to k into L power A, M power B, G power C. We now need to find the values of A and B using dimensions of the physical quantities on both sides of the equation. The dimensional formula for time is T. The dimensional formula for length is L. The dimensional formula for mass is M. The dimensional formula for acceleration due to gravity is Lt power minus 2. The constant does not have any dimensions. Hence, the dimensional formula of the quantities on the right side of the equation is simplified as shown. Let this be equation 1. The dimensional formula of the quantity on the left side of the equation is as shown. As we do not have the term for M and L on the left-hand side of the equation, we take their powers to be 0 as shown. Let this be equation 2. Equating equations 1 and 2. We compare the powers of the base quantities on both sides of the equation. Thus, we get B equal to 0, A plus C equal to 0 and minus 2C equal to 1. On simplification, we get the values of B equal to 0, C equal to minus half, and A equal to plus half. Thus, the expression for the time period of the simple pendulum becomes 2 pi into the square root of L by G as shown. The value of K, which is equal to 2 pi, cannot be found by using dimensional analysis. However, this method cannot be applied to derive equations where addition or subtraction of different terms is involved. For example, we cannot derive the equation S is equal to ut plus half at square using dimensional analysis, even though we checked its dimensional consistency. Dimensional equations can be used to convert units of a given physical quantity from one system to another, and to thus find the conversion factor. For example, consider the physical quantity force. The dimensional formula of force is mLT power minus 2. The SI system of unit of force is Newton, and its CGS unit is dyne. Hence, 1 Newton is equal to 1 kilogram into 1 meter into 1 second power minus 2. Similarly, 1 dyne is equal to 1 gram into 1 centimeter into 1 second power minus 2. Now, we divide 1 Newton by 1 dyne and then find the ratio of Newton to dyne as shown. Thus, 10 power 5 is the conversion factor to convert Newton to dyne. Dimensions are generally used as a basic test to check the consistency of an equation, where there is a doubt regarding its correctness. However, this test cannot be completely relied upon, especially in the case of dimensionless quantities or functions. Dimensionless constants cannot be obtained by this method. For example, the arguments of some dimensionless functions such as trigonometric, logarithmic, and exponential functions cannot be obtained using dimensional analysis. The ratio of similar quantities results in a pure number, which is again dimensionless. For example, angle is the ratio of arc length to radius, which is length divided by length. Absolute refractive index of a medium is the ratio of the speed of light in a vacuum to that in a given medium, which is the ratio of speed to speed. The test of consistency of dimensions not only tells us the consistency of units, but also helps the user ignore the units to be mentioned and conversions among multiples and submultiples of units. If an equation is put to the consistency test using dimensional analysis, and if the equation fails, it means that the equation is proved incorrect. If the equation passes the consistency test, it does not mean that the equation is correct. Thus, an equation proved to be dimensionally correct need not be an exact equation, but an equation that is proved to be wrong dimensionally must be a wrong equation. The dimensional analysis method is very useful in drawing relationships between various interdependent physical quantities. This analysis can only test dimensional validity, but not the exact relationship between the physical quantities in any given equation. The dimensional method cannot differentiate between physical quantities which have the same dimensions. For example, even though the quantities energy and torque have the same dimensions. They are completely different in every sense.